Good afternoon. So, yesterday we were discussing some of our methods, sampling methods, and in the process we had discussed certain the types of the sampling methods using which we can draw samples, and there are of two types like probability sampling and non-probability sampling, and we have discussed the probability sampling methods in detail. So today we will be discussing the topic like sampling distribution. Suppose say we have drawn the repeated samples, then basing on their pattern means how the variables of that sample will be calculated or the parameters can be which they will be how the mean or the variance of the sample will be distributed. So, what exactly is a sampling distribution is the probability distribution of a statistic obtained from repeated samples from the sample size drawn from a population. So, we are drawing repeated samples from a population. So, your sampling distribution is a probability distribution of a specific statistic, like suppose say we have drawn several samples, the sample values like x1 to xn, each one is a sample statistic. The mean of it is a sample statistic, variance of it is a sample statistic. So a sampling distribution is a probability distribution of a statistic obtained from repeated samples of the same size drawn from a population. So any quantity computed from sample values like x1, x2 and xn, so on. These are our sample variables or sample values. So any quantity computed, that means maybe a sample mean, maybe a sample variance, maybe a sample proportion, each one is a sample statistic. And since it varies from sample to sample, it is a random variable, so with its own distribution. Okay, so the sample mean, we know it is the average of your observed values. Sample variance we have discussed earlier, that is the spread of our observations is called as your variance, and proportion is the ratio of successes. Okay, so next is why we study the sampling distributions. So if we know the probability distribution of a sample statistic, we can calculate the probability that it falls in any given interval. This is the foundation of all statistical inference. The sampling distribution is the probability distribution of the sample statistic that we are calculating the probability that it falls in any given interval. This is the foundation of all statistical inference. Okay, that is, one is your hypothesis testing, that is determining if observed results are statistically significant or due to chance, or the confidence intervals, that means whether the estimated population parameters are within the known precision levels, that levels are admissible levels, we call it as confidence intervals. And decision making, this is making data driven decisions backed by probability calculations. For this purpose, for hypothesis testing, for making whether our population parameter estimates are within our precision levels or not, and whether basing on the data that we have driven, we will be taking the decisions which will be backed by our probability calculations. So for this purpose, we are required to study our sampling distributions. So how it works? First of all, as usual, we have to define the population, all items of our interest, past and future. Then we need to draw the sample based on a sample size, maybe select 10 items randomly from the population. Then compute the statistic, that means compute the sample mean or sample proportion and sample variance. Repeat and observe the distribution of statistic emerges. So if we will be repeating, then we will be getting the distribution of that particular sampling mean or sampling variance or sampling proportion. Suppose say a machine fills containers automatically. The population is all filled containers, past and future. So we draw a sample of n containers, weigh each one and compute the sample mean of the weight. Repeating this process many times reveal the sampling distribution of the mean. Okay. So, putting into practice, suppose say a talcum powder brand preference, the scenario is that 45% of users currently prefer this particular brand and 60% of 100 users prefer the new version. So, is the 15-point jump real or just a sampling error? Whether this 15% jump is real or the sampling error. We need the sampling distribution of proportion to answer this. Suppose say the probability of sample more than 60% is large. That is, for example, it is 0.5. The high sample proportion could easily occur by chance. So the new version may not be superior. But if the sample is greater than or equal to 60% is tiny or small, which is maybe negligible, that is probability is 0.001. This result is extremely unlikely by chance alone. So this new version is likely genuinely preferred. So depending upon this value, we can say either it is preferred or it is not preferred. So that is the sample statistics. What are the things that we have so far discussed? The sample statistics are random variables. They vary from sample to sample and have their own probability distributions. So knowing the sampling distribution, let us calculate the probability of observing any particular result. This probability drives, that is, once we calculate the probability of observing any particular result, then we will be in a position to drive our inferences based on the hypothesis testing or confidence intervals or any evidence based decisions. So a very low probability for an observed result suggests the underlying population parameter has shifted. Okay, a very low probability suggests that the underlying population parameter has shifted. So the sampling distribution is the bridge between data and decisions. So whether it is matching your population parameter or not, how far it is deviating, to discuss that or to study that is your sampling distribution. So how accurate your sample is, to decide that we are required to have our sampling distribution. Okay, next. The role of your probability in this inference, since sample statistics form the basis of all inferences drawn about populations. If we know the probability distribution of the sample statistic, then we can calculate the probability that sample statistics assumes a particular value. It may be a discrete or a random variable or a continuous, or has a value in a given interval, that is a continuity. So this ability to calculate the probability that the sample statistic lies in a particular interval is the most important factor in all statistical inferences. So let us demonstrate this with an example. Suppose say testing a new improved talcum powder formula. So non-population proportion is 45%. Sample result, when we are taking a sample of the size 100, it is 60%. That means known population proportion is that 45% of all talcum powder users currently prefer the brand over the competing brand. Whereas the sample result says that of the random sample of 100 users preferred the new improved version. Okay. The question is, what is the probability that the sample proportion is as large as 60% or higher when the true population proportion is only 45%? The answer will be, if the probability is large, The high sample proportion of 60% could easily occur by chance due to sampling error. The new version is not necessarily superior to old. But if the probability is very small, for example, say it is 0.001, rather than concluding, we observe rather a rare event and we conclude that the true population proportion is higher than 45% and the new version is genuinely superior. So if the probability is large, we say that the new version is not necessarily superior to the older one, but if the probability is less, very small, then we say that the new version is genuinely superior. So to make this determination, we need to know that sampling distribution of the proportion, the probability distribution that tells us how sample proportions behave when drawn from a population. So sampling distribution of the mean properties, derivations and the central theorem we will be discussing next few slides. So why this sample mean matters? Of all sample statistics, the sample mean is the single most important tool in statistical inference. Here is why it deserves a special attention is that it is the most widely used estimator. Nearly in every field, suppose say in quality control to clinical trials experiments, we realize on the sample mean, that is x bar, to estimate unknown population means. So we use the sample mean to estimate the unknown population mean. Understanding its distribution is the gateway to interpreting any sample based results. And the number two reason is that it is having a predictable behavior. Unlike individual observations, the sample mean has two elegant properties. Its expected value always equals to the population mean that we have discussed while discussing our probability distributions, that your sample mean, expected value of the sample mean is always equal to the population mean. In that case, it is, we say that our sample mean is unbiased one, and its spread shrinks systematically as the sample size grows. Okay, and foundation of all inferences, that is confidence interval, whether it is confidence interval or hypothesis testing or any p values, all depend on knowing how your sample mean is distributed. Everything depends on the sample mean distribution. Without sampling distribution of the mean, none of the modern statistics we can work. So we'll derive the sample mean, we'll say exactly how the sample mean behaves, the mean of the sample mean, variance of the sample mean, and remarkable central limit theorem we will be discussing next. The sample mean as a random variable, when we draw a sample mean of the size n from a population with mean mu and variance sigma square, the sample mean is defined as x bar is equal to 1 upon n summation xi, where I varies from 1 to n. Okay, so mean x bar, that is the sample mean, is equal to the population mean, and the standard error of the sample mean is equal to the population standard deviation divided by square root of n, where n is your sample size. So the expected value of the sample mean is always equal to the population mean. This indicates that your x bar or the sample mean is unbiased estimator of your population mean. And your standard error is equal to the standard deviation divided by the square root of n, where n is the size of the sample. So the standard deviation of the sample mean shrinks by factor of square root of n. That means larger the sample size yield more precise the estimate of your standard error. So how can we derive those things? This is these are the simple steps. So definition of expectation of x bar we have discussed previously, and that is expectation x bar is equal to expectation of 1 upon n and summation xi. By taking the linearity property of our expectation, we can say this is equal to 1 upon n expectation of x1, expectation of x2 and so on expectation of xn. So each expectation xi is equal to mu, so it will be n mu divided by n is equal to mu. So since your variables x1, x2 and xn are drawn from the sample population, each has the same expected value of mu. Okay. Similarly, variance of x is equal to sigma square, a variance of x bar sample mean is equal to sigma square by n. In the same light, we have derived it and it is equal to sigma by square root of n. These are the simple steps. So key requirement is that x1 to xn, meaning all these variables x1, x2 and so on xn are independent, and variance of ax is equal to a squared variance of x, which pulls the 1 by n out as 1 by n square. That means we know that variance of ax is equal to a square into variance of x. That is the property of your variance. Next is your central limit theorem. So if all your sample variables, that is x1, x2 and xn are IID, matlab identically and independently distributed random variables. Okay, all these variables are independent and they all are identically distributed. Random variables with expectation xi is equal to mu and variance of xi is equal to sigma square, where your sigma square is less than infinity. That means your variance is finite and the size of the sample, that it tends to infinity. If it is very large, in that case your sample mean, this will be a standard normal variable. Z is equal to x bar minus mu divided by sigma on root n, which is will be standard normal distribution with, and we know that standard normal distribution or G is having a mean 0 and standard deviation 1. So the population must have finite mean and finite variance. This is the only distributional requirement for your central limit theorem. Independence, that means all the observations drawn must be independent. They are satisfied by random sampling or sampling with replacement method, and your sample size should be large, more than 30. Okay, convergence improves with n for symmetric population. If n is more than or equal to 15, often suffices, but for skewed distributions, it should be more than 30 is the common guideline. So, okay, the central limit theorem is a fundamental one concept in statistics which explains how the distribution of sample mean behaves when we take repeated random samples is sufficiently large, usually n more than 30. Then the sample means distribution will be normally distributed regardless of the underlying population distribution, whether it is normal, skewed or otherwise. This central limit formula says that the sample mean will approximately a normal distribution, which is given as the sample mean x bar is approximately a standard normal distribution, a normal distribution with mean mu and variance sigma. Sigma by square root of n is the standard deviation. So your central limit theorem says that as it tends to large, or you may say the sample size is large, the sample mean minus mu divided by sigma upon root n is a standard normal distribution. This is the formula of your central limiter. So next is your sampling distribution of variance, the chi-square distribution and inference about variability. Here we will be discussing just the concept about the chi-square distribution, and in the perhaps the last module or last block unit of this particular block, we are having a detailed discussion on chi-square. In that, we will be discussing the detail about the chi-square distribution and how can we perform the chi-square test. Okay. So why your sampling variance or sample variance matters? Knowing the center is only half the story. We know while discussing the variance, during that we discussed that if the samples are so taken, then the center or the mean of each of the sample may be equal. So to compare your samples or to compare the observations and make a decision, we need to have one more variable to be calculated, that may be the sample variance. So knowing the center is only half a story. Understanding variability tells us how reliable our data is and how much uncertainty surrounds every estimate. So number one is quality control. So your manufacturer needs variance within tight bounds. A machine may hit the target perfectly, but excessive variability still produces defective products. Performing risk assessments in finance and engineering, your variance quantifies risk. Two investments with the same expected return can have vastly different risk profiles based on variance. And prerequisites of other tests may be many inferential procedures like your t-test, analysis of variance test, regression analysis, assume equal or known variances. So testing these assumptions require your sampling distribution of the variance, sample variance. So to make inference about variance, we need to know about the sample variance. S square behaves across repeated samples. How this sample variance behaves across repeated samples is to be known. So sample variance, we say it as S square. So for a random sample x1 to xn from a population with mean mu and variance sigma square, the sample variance is equal to 1 upon n1 n minus 1 summation xi minus x bar whole square. I hope you remember we have calculated this while discussing our variance. So where I is equal to 1 to n. This is the formula we have discussed during that period, and again why we divide it by n minus 1, that also we have discussed during that period. The deviations are constrained by summation xi minus x bar is equal to 0. We have a property over there that if you will be the difference between the sample value minus the mean and the summation of all the samples values minus the mean is equal to 0. So once n minus 1 deviations are known, the last is determined. Okay, so only n minus 1 values are free to vary. So dividing by n minus 1 instead of n corrects the systematic underestimation that occurs when using x bar in place of mu. Okay, like your sample mean, your sample variance is also a non-biased estimator of your population variance, that is expectation of your sample variance is equal to the population variance. The sample variance is an unbiased estimator of the population variance. This holds regardless of the underlying population distribution. Whatever may be the underlying population distribution, Your sample variance is always the unbiased estimate of the population variance. So over here we are simply discussing the chi-square distribution. So suppose say the definition is that Z1, Z2 and Zk are independent standard normal random variables. By standard normal random variables I mean each of these random variable is drawn from a standard normal distribution. That is, each G1 or G2 and Gk are standard normal distributions. They are drawn from standard normal distributions. In that case, your chi-square is equal to sum of all this, and it is the chi-square with k degrees of freedom. Okay, as because they are k numbers, so it is k degrees of freedom. So since your chi-square is sum of squares, it can never be negative, and the distribution is defined only for values which are positive. And your chi-square distribution is asymmetric, skewed to the right, and as k is your degrees of freedom, it increases, it becomes, as k increases, it becomes more symmetric, and as the k becomes very large, your, you may say, curve will be bell shaped, that is normal, will be approaching your normality. And mean of your chi-square or expectation of your chi-square is equal to the k, that is the degrees of freedom or the number of observations on a sample site, and variance of chi-square is equal to 2ak. The expected value equals the degrees of freedom and the variance equals the twice the degrees of freedom. Both grow linearly with k. So as k becomes large, your chi-square distribution will be approaching the bell-shaped or normal distribution. So explaining it further, it is basically being used for, you may say, these are independent standard normals. Your chi-square is summation of gi squares, where gi, I from 1 to k, and each of the gi is a standard normal variable, and all g's are independently drawn from the same g standard normal distribution. So k, the number of observations or the sample size, is equal to the degrees of freedom. So always it is non-negative, right skewed, approaching normality as k grows, mean is equal to k, variance is equal to 2k, and the shape depends entirely on the degrees of freedom. As the degrees of freedom increases, it will be normal. So it is basically being used for goodness of fit and test of independence, and the inference about the variance we will be discussing it in detail in our fourth, the 10, 11, 12th unit. Okay, build confidence intervals and hypothesis tests for population variance sigma square. So chi-square changes with the degrees of freedom. As the degrees of freedom will increase, it will be the bell shaped. So when k is equal to 2, exponential shape, k is equal to 8, visible skew, and k is equal to 30, nearly bell shaped. Okay. So as k increases, chi-square distribution shifts right and spreads out and becomes more symmetric, eventually approaching a normal distribution. So deriving the distribution of S square, it is the algebraic identity decomposes total variation into within sample variance plus the squared standardized. So it is, the result is that n minus 1 S square by sigma square is chi-square n minus 1. This result requires the population to be normal. It is the basis for chi-square tests on variance. Suppose say a machine is, small example working out, a machine fills containers with sigma square is equal to 144 gram square. So sigma, that is standard deviation, is equal to 12 gram, and a sample of n is equal to 25 yields s square is equal to 200 grams. So is the variance significantly higher than claimed? So it is asked that we should take the tolerance limit as 0.05, or you may say the confidence interval as 0.05, or 500% level of significance. Okay. So test statistics is n minus 1 s square by sigma square. So n is our 25, 25 minus 1 is 24, to 200 divided by 144, that is equal to this much. Our degrees of freedom is 25 minus 1 is 24. So critical value as per our table, we will be getting it from the chi-square tables. It is chi-square for 24 degrees of freedom at 5% level of significance. The tabulated value is 36.415, but our calculated value is 33.33. So your calculated value is less than your tabulated value. So we say that at the 5% level of significance there is insufficient evidence, as because your calculated value is less than your tabulated value, we say that the evidence is insufficient to conclude that the population variance exceeds this. Sorry, sample variance exceeds the population variance. So next is your F distribution. When you are comparing variances, two variances from two independent populations, we need a new distribution built from the ratio of two chi-squares. So suppose say U is a random variable which follows a chi-square distribution with the d1 degrees of freedom, and V is another random variable which is again a chi-square distribution with d2 degrees of freedom. They are independent, then your F will be U by d1 divided by V by d2. Okay. So, two degrees of freedom parameters, d1 from the numerator sample and d2 from the denominator sample, each controls the different aspect of the same. So comparing the variances, your S1 square and S2 square, if the two populations have equal variance, then your F will be equal to 1. It is used everywhere, that is your analysis of variance, regression, significance tests, and equality of variance tests all rely on your F distribution, wherein your F is a ratio, both the variables of your numerator and the denominator, they follow the chi-square distribution with different degrees of freedom. So two, again over here, suppose say we are taking a F test for two variances. Two filling machines produce containers. Machine A having this N1 is equal to 16, but the sample size is 16 and variance is 220, and B sample size is 21 and variance is this. So at 5% level of significance, is machine A's variance significantly greater than machine B's variance? We have to decide about whether machine A's variance is significantly greater or machine B's variance is significantly greater. Okay. So we may say our hypothesis is that sigma 1 square is equal to sigma 2 square versus sigma 1 square is more than sigma 2 square. It is one tail, right tail test. F is equal to S1 square by S2 square. It is 220 by 110 is 2.2. So our degrees of freedom is 15, 20. So your F value at 5% level of significance, 15 and 20 degrees of freedom is equal to this. This is again your tabulated value. So your calculated value is 2 and tabulated value is this. So calculated value is less than the tabulated value. So we don't have, so or else you may say We are having insufficient evidence to conclude that machine say variance is significantly greater. So confidence interval using chi-square distribution to bound population variance. You may say the larger the critical value appears, the lower bound denominators and producing smaller endpoint and inversion unique to variance intervals. Next is the t distribution. It is the central limit theorem gives that our z is equal to, that is your standard normal variable is having this formula. So, but this requires the knowing sigma. In practice, we almost never know the population standard deviation. So, we must estimate it from the sample. If that is the situation, then your t distribution comes into existence. So your problem is that z value is this, it requires sigma, but we rarely know it. Simply plugging in s introduces extra randomness, the ratio is no longer standard normal. So your William S. Gossett, the pen name is student, or you may say pseudonym is student, shows that t is equal to x bar minus mu divided by s L by square root of n, follows a specific distribution that is called as the t distribution, which accounts for extra uncertainty from estimating sigma with s. So replace sigma with s, that implies that replace the normal with t. Okay, that is, we already proved that n minus 1 s square by sigma square is a chi-square distribution with n minus 1 degrees of freedom, and that your mean and standard deviation, or you may say sample mean and sample variance are independent when the population is normal. So your t distribution emerges directly from these two results. It is the ratio of standard normal to square root of chi-square divided by its degrees of freedom. Okay, g divided by square root of b by k is a student normal distribution. G is standard normal variable and V is your chi-square with k degrees of freedom. Okay, so for inference about the mean, your t is equal to this much. So your t distribution, like normal distribution, is bell shaped and centered at 0. Expectation of your t statistic is equal to 0 when k is more than 1. And variance of k t is equal to k by k upon k minus 2, which is greater than k1 for k is more than 2. So the extra variance from estimating sigma produces fatter tails than the normal, making extreme values more probable. So it converges as k tends to infinity, your sample variance or sample standard deviation tends to the population standard deviation, and the t distribution converges to standard normal distribution with mean 0 and variance 1. So for k more than 30, the difference is negligible in practice, or you may say if your sample size is more than 30, then your t distribution tends to the standard normal distribution. So deriving t statistics, this is the derivation which requires normality. The sigma cancels in the ratio, so the t statistics depends only on observable quantities, that is sample mean and sample standard deviation, never on the unknown sigma. So how t changes with the degrees of freedom? As degrees of freedom increases, your sample standard deviation becomes better estimate of your population standard deviation. The extra tail weight shrinks and the t distribution gradually approaches your standard normal distribution. Okay, so when your k is equal to 1, it is Cauchy, you may say, extremely heavy tails, no finite mean or variance, rarely used in practice. But if your k is between 5 and 10, or The smaller samples, noticeably heavier tails than the normal. Critical values are larger, wider confidence intervals reflect extra uncertainty for small n. And when k is more than 30, it is normal, nearly indistinguishable from standard normal variable, and t is 2.042 at k is equal to 30 versus 1.96 standard normal variable. That means this is the difference between these statistics and standard normal variable when it is more than 30. So only 4% difference. So key properties of your t distribution: expectation of the t statistics is equal to 0 for k positive, variance is k by k minus k upon k minus 2, and the shape of your t distribution is symmetric, bell-shaped, unimodal like the normal but with heavier tails. And limit when k tends to infinity, your t tends to standard normal distribution. This is a worked out example. Okay, so confidence interval interpretation, continuing the fill-weight example. These are some of the practical problems, and this is the summary of the distributions that we have just discussed. Comparing, you may say, the four that we have discussed so far. One is your standard normal, one is your chi-square, one is your f, and one is your student's t. And your normal, standard normal, when sigma is known, mean is known, and statistic is z is equal to sample mean minus population mean divided by sample standard deviation upon square root of n, where n is the size of the sample. This is the foundation for all others derived from normal samples, where chi-square testing or estimating variance, sigma square is inference, confidence interval for variance, and statistic is n minus 1 s square by sigma square is the chi-square distribution with n minus 1 degrees of freedom. Sum of squared normals, major spread, and this is the variable which is always positive. It is the sum of squares, so always positive. F distribution, it is used for comparing two variables. It is called as your analysis of variance. The ratio of two chi-square variables, it compares the spreads between two variables. And student's t, it is basically being used when your standard deviation is not known. Most real problems, the test is the mean, sigma is unknown, confidence interval for mu, that is population mean, and statistic is t is equal to x sample mean minus population mean divided by sample standard deviation upon square root of n. So it is g is equal to this, which replaces sigma with s. So all these are built from your standard normal variable, that is, or standard normal distribution, that is the normal distribution with mean 0 and standard deviation 1. Next is your interval estimation from point estimate to confidence intervals. A point estimate gives a single best guess for a parameter, whereas your confidence interval adds a measure of precision, a range of plausible values with a stated level of confidence. The general form is that point estimate plus and minus critical value into the standard error. This is the formula for your confidence interval. Point estimate, our single best guess may be your sample mean, sample variation, or the p-value, the center of the interval. Critical value is, it controls the confidence level. Confidence level may be 5%, 10%, that is the G alpha by 2, T alpha by 2, that is, as because there are two tail tests, so your level of significance is divided by 2, that is 0.25, 0.25. It is also 0.25, 0.25 and chi-square values. Higher confidence, the wider the intervals. The standard error is measures sampling variability, sigma by square root of n or sample standard deviation by root over n. More of the data, smaller the standard error, narrower will be your confidence interval. So what 95% confident really means, we repeat, if we repeated the sampling process many times, about 95% of the intervals we construct would contain the true parameter. Any single interval either contain the parameter or it doesn't. So the 95% is a long run frequency statement about the procedure, not the parameter. So confidence interval for your population mean given your standard deviation, population standard deviation is your sample mean plus or minus the jet value into alpha by 2. By this is alpha is your level of significance into the standard error. The population is normal, the sample size is more than 30. By central limit theorem, it is a standard normal distribution. So your sigma is known and sample is random. So for example, suppose say your manufacturer knows that standard deviation of is 3.5 mm, a sample of 49 parts has sample mean of 80.2 millimeter. A confidence interval we have to find out for our population mean. Our standard error will be the sigma, that is the 3.5 divided by the square root of n, that is 49 of square root, that is 3.5 by 7 is this much. And critical value is the G value at 5% level, one tail of 5% level of significance is 1.96 and margin of error will be 1.96 into this is equal to this. So your 95% confidence interval is 80.2 minus 0.980 and 80.2 plus this. So your width depends on three levels. Increase n, if n value increases, it will be narrower. If your sigma value will be reduced, it will be narrower, and lower confidence level, then it is narrower. In that case, we say it is riskier. Confidence interval of mu of sigma known if it is your t statistics following the same procedure, we can say that this is the confidence interval for my mean. And this is if my variable is chi-square. In that case, this is the confidence interval calculation. So choosing the right interval, estimating mu with sigma known, your standard normal interval, your sample mean plus z alpha by 2 into sigma. This is symmetric, requires known sigma. It is rare in practice, whereas in case of t intervals, this is the thing where your distribution is symmetric, where wider than z, most common in practice, and estimating sigma square or sigma, your chi-square interval, this is the value, and comparing two variances, your f will be the statistic. In that case, it is asymmetric, contains 1, which is implies and implied by variances not significantly different. So what is the parameter? Then you first of all have to decide about what is exactly the parameter, what that parameter follows which distribution. Then we have to decide about whether our sigma, we have to know whether the sigma is known or unknown. then we have to pick the distribution and accordingly we have to calculate the interval. So sampling distribution of proportions. So from counts to proportion. If X counts successes in n independent Bernoulli trials, then p value, estimate of p is equal to X by n. What is that Bernoulli trial? That means in that we are having two variations. One is 0 and one is 1. Okay, so mean of your Bernoulli distribution is equal to P and variance is equal to P into 1 minus P by N, where N is your number of trials. And the standard error is the square root of your variance, that is square root of P into 1 minus P divided by N. So your P estimate is an unbiased estimator of the true proportion if expectation P cap is equal to the P. That means if the sample mean, expectation of the sample mean is equal to the population mean, then your sample mean estimator is an unbiased estimator of your population mean. So your P cap is an unbiased estimator of the true proportion P. Okay. And variance is variance of P cap is equal to P into 1 minus P by N. It shrinks. That means as your N grows, if N tends to infinity, no, this will be smaller. No, as because it is the denominator, as the denominator grows, the proportion is maximized. So shrinks as N grows and maximized at P is equal to 0.5. So standard error, it controls the width of the confidence interval for P. So key insight over here is this is connection to binomial. Your P cap is equal to X by N, where X is a binomial distribution. X follows a binomial distribution, okay, with the parameters N and P. Every property of P cap follows directly from the binomial. So your maximum variance at P is equal to 0.5. This is why conservative sample size calculations assure P is equal to 0.5. It gives the largest possible standard error. So maximum variance at P is equal to 0.5. Why? This is why the conservative sample size calculations assume P is equal to 0.5. It gives the largest possible standard error. Analogy to your sample mean over here is that just as the sample mean estimates your population mean with standard error, population standard deviation divided by square root of n, your P cap estimates the value of the P with standard error square root of P into 1 minus P by n. So normal approximation for your P cap is equal when n is large enough. Okay, when your sample size is very large, when your n tends to infinity, in that case your P cap, that means the estimate of P is equal to the normal distribution with mean P and variance P into 1 minus P by n. So conditions, rule of 10 we say here is NP is more than 10, n into 1 minus P is also greater than or equal to 10, and our sampling is random sample. The standardization is equal to, over here, we can standardize it as P cap minus P by square root of P into 1 minus P by n, and this will follow a standard normal distribution with mean 0 and standard deviation 1. Suppose say a factory has a defect rate of point P is equal to 0.08. In a sample of 200 items, what is the value that probability of p cap is more than 0.10? So first of all, check the condition, that is NP is equal to 200 into 0.08, which is equal to 60, okay, which is greater than 10. So N into 1 minus P is equal to 200 into 1 minus 0.08, that is 0.92. 1 minus P is equal to 184, which is also greater than 10. And the sample that we have taken is random sample only. The standard error over here is 0.08 into 0.92 by 200 is equal to this much. So your G score will be 1.043. So what will be this probability then? This is equal to probability of G is more than this. This is equal to this that we have calculated. So by taking our tabulated value, this is 1 minus 0.8585. This is equal to this. This you can get from the standard normal distribution tables, which are available on each and every statistics book appendix. Okay, so confidence interval for a population proportion, your condition is that confidence interval, you know, that is P estimate plus or minus the G value at the level of significance. Okay, it is one is right tail and one is left tail into the standard error. The conditions is that NP is more than 10, N into 1 minus P cap is more than 10, and my sample is random sample, and N is less than or equal to 10% of my population. Okay, so for example, a poll of N is equal to 500 voters finds that 280 support a policy. This build a 95% confidence interval for the true proportion P. Okay, so the sample proportion P cap is equal to 280 divided by 500. So standard error will be equal to 0.56 into 0.54, that is 1 minus 0.56 divided by 500, that is equal to this. Okay, so critical value, the G value at the level of significance, 5% level of significance, one tail is equal to 1.96. So margin of error is E is equal to 1.96 into 0.02219 is the tabulated value. Sorry, this value. This is the tabulated value and this is the standard error that we have calculated. So it will be this. So 95% confidence interval will be 5.560 minus 0.044 and this 0.4 as 3.5, I have taken it as 4. Okay, and this is the confidence interval. Unlike the confidence interval for population mean, use the P cap in the standard error formula because P is unknown. This is the Boiled interval, a quick, widely used approximation. Okay, so next is how can we determine the sample size? How many observations do we need? The sample size for estimating mu is the idea, set a margin of error as E, which is equal to this to a desired maximum, then solve for N. Okay, we need to specify desired margin for our error, confidence interval level, and estimate of sigma. The key rules are always round N up, and having E requires 4x the sample size and sigma unknown and your S from a pilot study. So if we will be taking a small example with the critical value as 1.96, then our roundup will be 89 tablets. So for 99% confidence interval, we will be requiring this precision cost more at higher confidence. Okay, and similarly, sample size for estimating P, the formula will be n is equal to z alpha by 2 square into p cap 1 minus p cap divided by e square. If no prior estimate of p is available, then always use that p cap is equal to 0.5, which we consider as a conservative value to maximize our n. Okay, sure. The quick reference for your sample size may be estimating a mean mu. Your sample size should be like, the formula is this, requires your sigma or an estimate from the pilot study, n scales with sigma square, and having E requires 4x the sample size. And while estimating the proportion P, your sample size should be this. Summary maybe. So today we have discussed the sampling distributions. We have described how sample statistics, mean, variance and proportions behave across repeated samples, forming the basis for all our statistical inference techniques. And we have discussed the central limit theorem, the sample mean approach normality as n grows, enabling Z-based inference, and we will discuss certain variance and F distributions, which will govern inference about variability through chi-square and F-test, and we discuss confidence interval using our standard normal, T and chi-square and F distributions, and finally we are through with how we can determine the sample size, which leads us to calculate the number of observations that we need to achieve a desired precision for both means and proportions. So this speaks about how can we, from data to decisions, the sampling distributions makes everything possible. Thank you.